Hello, let's talk about linear differential equations. So here I have the forms for linear differential equations. And there's the general linear form, a of t y plus b of t. If the a of t function is just a constant, usually we use the letter lambda for that, then we call it a constant coefficient. If the b of t term is 0, we call it homogeneous. And if b of t is non-zero, it's called non-homogeneous. So that applies the same way to the constant coefficient case. We would say that a function is homogeneous constant coefficient when this b of t added on term is 0, and that it's non-homogeneous when the b of t term is 0. So the first thing I want to look at is the linearity principle, which applies to homogeneous equations. So here I've got the general homogeneous equation, and I've proceeded through following separation of variables properties to try to start solving it. You can see that generically, sort of in the abstract case, I might not actually know what the antiderivative of a of t dt is, or of a of t is, and therefore I've tried to sort of write it informally. But let's suppose we did have some function, capital A of t, which was an antiderivative for that a of t appearing in my ODE, and therefore that capital A of t plus generic constant c could be representing the indefinite integral. In that case, we can come up with a constant to replace the e to the c part, drop the absolute values with a plus or minus, and so solutions obtained from separation of variables would be plus or minus a case of 0 e to the capital AT. But also, since this equation, being separable and being of the form function times y, would equal y when I replace y, or would equal 0 when I replace y with 0, we have that y of t equals 0 is an equilibrium solution. Therefore, the separation of variables technique generates the following solutions once we fold in the equilibrium. That y of t could be some big constant of any plus minus 0, as long as it's real, times e to the at. So we have this reason to believe that the general solution to these homogeneous equations should be a constant family parameterized just by a constant multiple. The linearity principle affirms that this is the case. For a linear differential equation that is homogeneous, if we find one non-zero solution to that equation, such as written here y sub h of t, h for homogeneous, then any constant multiple of that solution is also a solution. And the proof follows from the constant multiple rule. Secondly, we have the extended linearity principle. And the extended linearity principle states that when we have a non-homogeneous equation where that b of t is 0, and we look at what we call the associated homogeneous, just the a of t y part, then let's take a solution y1 that solves the non-homogeneous, and a solution y sub h, which solves the homogeneous. So I've written there the information that would tell us they were solutions to those two equations, that the derivative of y1 is in fact a of t times y1 plus b, and the derivative of yh is in fact a of t times yh. Then if I add these two functions together, we do get that their sum will solve the non-homogeneous equation. So you can see I've replaced y1 prime on the second line with a of t y1 plus b, and yh prime has been replaced with a of t yh. Once we regroup the two terms that are both multiples of a of t, we get a of t times the sum plus b of t. And any function where its derivative is equal to a of t times itself plus b would be a solution to this non-homogeneous equation. So extended linearity principle says that we can find solutions by taking the sum of non-homogeneous and a homogeneous solution, and we'll get another one. But we can go even further with this, because it's not just that generates another non-homogeneous solution, but that actually is the way of generating all of them. And the reason for that is the following. Say we take two solutions. If we take two solutions to the non-homogeneous case and I added them together, I would not get another non-homogeneous solution. I had to add a homogeneous plus non-homogeneous to do that. But I can take their difference. So the difference of the derivatives of these two non-homogeneous solutions. And so I've formally done that here. So a of ty1 plus b minus a of ty2 plus b. And when I do that subtraction, the two b of t terms cancel one another. So what I'm left with is that the derivative of difference of homogeneous solution 1 minus the difference of non-homogeneous solution 1 and non-homogeneous solution 2 is a of t times that difference. Therefore, the difference of two non-homogeneous solutions is homogeneous. So the exact spacing between any two solutions to a non-homogeneous equation is a homogeneous solution. And under that, I discover that every homogeneous solution has to have the same form, and every non-homogeneous solution has to have the same form. So these are those general forms. The general solution to a homogeneous differential equation is a constant multiple of a homogeneous. And the difference in the general form of a non-homogeneous, this is the subscript notation that's typically used, is a sum of a particular solution to the non-homogeneous linear equation. So it solves some IVP and the sum with a general non-homogeneous. So making that by taking particular non-homogeneous solution and adding it to constant multiple of a non-zero homogeneous. And that will generate the solutions to the non-homogeneous equations. Those are those principles, and we'll see them in action.